Build an analog computer simulator for $4. A Raspberry Pi Pico will be transformed into a learning system that will behave like an analog computer, less all the patch cords. A second version with real-time analog I/O can be made for about $25 more. Before we delve into the digital world, let's have a look at what an analog computer is. Analog computers are systems made of components that behave like parts in other systems. Electrical, mechanical, thermal, chemical, and hydraulic systems have components with identical behaviors. For our computer, we use common electronic components. Voltage represents some value. The value can be anything: distance, height, pressure, temperature, speed, etc. First, we need a method to measure the value. A moving coil amp meter or galvanometer will be converted to measure voltage. The meter must measure both positive and negative voltages. When connected, it should have little effect and not load the circuit. The meter coil resistance and a selected 99.6K resistor add to 100K. The two diodes protect the meter from an overvoltage event. It is important to note the range of the meter is limited to plus and minus 10 volts. When working with analog computers, problems may require scaling to fit the range of the system. Our simple computer will use 9-volt alkaline batteries as the voltage source. Batteries can be stacked in series to obtain higher voltages. The first computation we need is division. A simple Type B linear potentiometer, not an audio Type A taper, is used to divide a voltage. If the potentiometer is set midpoint, it divides by 2. Set it at a 20% rotation and it divides by 5. To set a voltage, attach a battery across the potentiometer and connect the meter between the wiper and the negative battery terminal. Don't worry about the meter resistance loading the circuit. Our examples use a constant load and the voltage measured will be correct. Addition is possible by connecting 2 battery potentiometer dividers in series. Adjust one divider to 2 volts and the second to 4 volts. Connect the negative battery terminal of the 4-volt divider to the wiper of the 2-volt circuit and measure the wiper of the 4-volt divider. The computation is 2 volts plus 4 volts equals 6 volts. Now that we can add and divide, it is possible to perform linear algebra. The analog computer will be set up to solve for x, using 0.5 times x minus 4 equals y, where y will equal -1. 3 divider circuits are used. The leftmost is used to set up a 10-volt calibration voltage. The next divider is set to 5 volts, which is multiplied by 0.5. The third divider flips the battery terminals to generate a negative voltage that is set to -4 volts. The leftmost potentiometer is adjusted until the Y output reads -1 volt. The Vx voltage on the wiper of the leftmost potentiometer is the value of x that is required to make y equal to -1. It reads 6 volts on the meter. We can set Vx to any value and measure y to obtain xy pairs for the line. So far, we have only looked at static problems. Analog computers can solve dynamic problems such as differential equations. These types of problems are generally set up using Laplace transforms. A Laplace transform simplifies analysis of a system by using algebra to perform calculus. Our simulation will be that of an exponential decay. This could be a hot cup of tea cooling down to room temperature, photo decay of a fluorescence compound, or height of a liquid tank draining with a laminar flow. To perform this simulation, an integration function is needed. Think of integration as the accumulation of something over time. Turn on the faucet for a bathtub. If the water flows at 1 gallon per minute, the tub will have 2 gallons after 2 minutes, 3 gallons after 3 minutes, 3.2 gallons after 3.2 minutes. If the water is turned off at 4 minutes, it will have 4 gallons at 4 minutes, 4 gallons at 5 minutes, and 4 gallons until the water is turned back on or the drain is pulled. In the electrical world, capacitors are near ideal integrators. They accumulate charge, amperes per second, and the voltage increases with the reciprocal of the capacitance. In the Laplace domain, integration is represented as 1 divided by S. Capacitors are represented as 1 divided by SC, where C is capacitance in farads. Reviewing the voltage divider formula, we see the voltage across R2 is dependent on the applied voltage and the values of R1 and R2. A similar dynamic voltage divider can be created by substituting a capacitor for R1. Substitute 1 divided by SC for the R1 resistance value and use the same formula. Notice the switch that is connected to the battery. It closes at time 0 and generates a step function. The input voltage to the capacitor jumps to the battery value and remains there after time 0. The Laplace of a step function, or simply V divided by S for our example. The equation must be arranged to a special form before the inverse Laplace can be applied. A partial fraction expansion is used to get to the needed form. Once in the correct form, the inverse transform brings us into the time domain where the result is an exponential decay from the voltage V to 0. Changing the RC circuit to a parallel connection plus a potentiometer makes it easier to set the starting voltage. Also, the capacitor does not need discharging before starting the experiment. The only difference is the input voltage starts at the adjusted battery voltage before time 0. Use a watch to measure the voltage over time. Set the meter to 8 volts, open the switch, and take readings for every 0.5 volts drop in voltage. Plot the time and voltage values in a spreadsheet to see the shape of the discharge voltage. Our simulation has an exponential curve with a time constant of 110 seconds. A time constant is the time from starting at 8 volts to dropping to 3 volts. 3 volts is 37% of 8 volts. The ideal time constant should be R times C, which equals 100K times 1000 microfarads, or 100 seconds. Our longer time constant can be attributed to something called dielectric absorption. Normally, high-quality film capacitors with low dielectric absorption are used for integrators, not the electrolytic type in our example, which measures 938 microfarads at 60 Hertz. The final analog circuit we will explore is a relaxation oscillator. For timing, it uses an RC circuit that charges and discharges. A device with hysteresis is required to control the charge-discharge sequence. One common electronic component with hysteresis is a relay. We have a relay with a coil rated for 12 volts DC. The pull in voltage, about 6.1 volts, and the dropout voltage is about 4.9 volts. The normally closed contact is used to energize the relay through a series resistor. When the pull-in voltage is reached, the contact will open, causing the normally closed contact to open. It operates like a buzzer. The contact is held open or closed for a longer time by placing a capacitor across the coil. The resistance of the relay coil controls the capacitor discharge. After 6.1 volts is reached, the normally closed relay contact opens and the discharge time constant is 333 times 4700 microfarads or 1.57 seconds. 4.9 volts is only 80% of the 6.1 volt starting value. Solving for the exponential, it takes about 0.35 seconds. The charge cycle is a bit different. The capacitor is charging from a voltage divider formed by the series resistance and the coil resistance. Charging starts at the dropout voltage of 4.9 volts and heads towards the divider voltage of 7.1 volts. At around 6.1 volts, the discharge cycle starts, then it heads towards ground. The resistance for the charge cycle is 330 ohms, in parallel with 110 ohms, or 83 ohms. The RC time constant is 0.39 seconds. Since the pull-in voltage is at 6.1 volts, or about 55% of the way, we need to solve the exponential. It should take about 0.31 seconds to go from 4.9 volts to 6.1 volts. The circuit is estimated to oscillate between 4.9 and 6.1 volts with a period of around 0.66 seconds. Looking at the meter, it is difficult to measure the oscillation period and the low and high values. Analog computers use strip chart recorders or oscilloscopes to plot fast-moving signals. Hopefully, you have a basic understanding of the simplicity of analog computing for solving problems. This video covers a simulator that runs on a Raspberry Pi Pico processor. Instead of wires connecting circuits, variables are used to connect blocks that add, multiply, integrate, and perform special functions. The simulator requires a serial terminal program to enter code and receive output data. A Windows-compatible terminal program, simplecrt.exe, is provided, or you can use your own. All resources are available on GitHub. Real-time analog input and output is possible with a simulator through PWM and the built-in ADC. A plus and minus 10 volts range is possible with some additional circuitry. The Pico, a USB cable, and your PC are all that's required to run simulations. On GitHub, click on the Code button, then download zip. Extract the zip folder and open the extracted block diagram compiler main folder. Find simplecrt.exe and copy it to your desktop. Hold the program button down on your Pico and plug the USB cable into your computer. This will open the Pico file system. Find Pico block compiler m.uf2 in the block diagram folder and drag it into the Pico file folder. On the desktop, click the Start button, which is the window icon, then click on the Settings icon. In the Find a Setting text entry box, type Device Manager and hit Enter. In Device Manager, click to expand ports, COM and LPT, and note the COM port number for the Pico. Go to your desktop and double-click on Simple CRT.exe. Windows may ask if you really want to run the program. Say yes. Select the COM port drop-down and select the COM port for your Pico. Click on the Open menu. The red box should turn green, indicating that the port is open. Hit the Enter key and the Pico will return an "I don't understand" and a 0 : prompt. The 0 is the current program line number. Program lines consist of a 3-letter function name, 1 or more input variables, and 1 or more output variables. Spaces to limit the fields and variables are no more than 3 characters long. There are no constants. Variables are initialized to 0, but can be assigned a value using the set command. Adding function blocks increment the program line number, but commands do not. Line editing is limited to using the backspace key to correct mistakes. If you want to change a specific line, at the prompt type LIN space, the line number, and hit Enter. Type in the new text. After hitting Enter, use the LIN command to return to the last line in the code. Let's simulate the previous analog computer examples. The simulator only has a text input mode. To help visualize the connections, a block diagram will accompany each program. Type in the program shown on screen. If you have a program in memory, you can clear all the program and variables by typing CLR and hitting Enter. The set block is a command. It is executed after hitting the Enter key. Set DT1 sets variable DT to the value 1. DT is a built-in variable used for the step time. Variable names can be numbers if it makes it easier to read. If a variable is not assigned a set value, it is initialized to 0 when created. After entering the program, type Run and press Enter. The answer to 2 plus 4 is 6. The program terminated because the variable max value was reached. Max is preset to 1 second. Since dt is 1 second, only one loop ran. The equation x divided by 2 minus 4 equals y is arranged to solve for x, where x equals y plus 4 times 2. Setting y to -1 solves x for this single point. Type in the program and run it. The answer is also 6, as with the addition program. By setting dt to 0.1, the program will run for 10 loops from 0 to 0.9 seconds. The summing block adds 1 to y each loop, and y will increment from 0 to 9. Use the CLR command to clear the program and variable space, then enter the program. The result is 10 XY pairs with y stepping from 0 to 9. For the exponential simulation, we need to see how an integrator works. The block compiler has 2 built-in integrators. EUL is a rectangular integrator and INT is a trapezoidal integrator. The rectangular integrator will serve as our example. By connecting the output of a summing function to its input, the output will increase by the input value each time a loop is executed. Our integration is with respect to time. Multiplying the input by the step time dt is the approximate area of the input function over time dt. When added to out is the integral of the input function over time at discrete steps of dt. Integration can continue until the out variable overflows. Adding a limit function inside of the feedback loops allows the accumulation to stop at a set value. If it were outside the loop, the summing function would continue to increase or decrease in value. A gain block is added to the input part of the integrator. When this is built into the integrator, it reduces the number of blocks needed for simulation. Before we proceed, some negative feedback theory is needed. For a gain circuit with gain G, feedback theory says the output divided by the input is G divided by 1 plus G. Any function can be substituted for the gain block and the equation still holds. To simulate an RC decay, negative feedback to the integrator is used. The feedback equation replaces the gain function G with the integrator function. The integrator is G divided by S because it has a gain input. The negative feedback for output input is G divided by S divided by 1 plus G divided by S, which equals G divided by S plus G. This is identical to the RC divider circuit Laplace form if we set G equals 1 divided by RC. Type in the program to simulate an RC decay. The integrator output is initialized to 8. Note that the maximum runtime is set to minus 250. If it is positive, the program runs real time and takes 250 seconds. The negative value runs the simulation at maximum speed. Run the program and it will provide 250 solution points. Simple CRT holds the last 256 lines of received text. Use the scroll bar to inspect the data. Clicking the plot button displays the data. Time goes from 0 to 250 seconds. Out decays from 8 towards 0. The edit boxes at the bottom of Simple CRT allow scaling and offset for the plot display. The final simulation is of the relaxation oscillator. The circuit had two separate states. The charging from 4.9 to 6.1 volts with a time constant of 1 divided by 0.637. The discharging from 6.1 to 4.9 volts with a time constant of 1 divided by 2.56. Charging heads towards 7.1 volts and discharging towards ground. Variables are reset using conditional branches. The output is tested for a limit using subtraction. As long as T1 is negative, BRM skips to the third instruction. Once positive, the integrator gain is reset to 2.56 and the input is reset to 0. The second conditional branch works the same except T2 must be plus for the reset to occur. This program is a bit longer, so use Notepad to generate a text file. Including CLR on the first line clears the system when the program loads. Having run, at the file end, starts it once it loads. Type in the file and save it as relay sim.txt. In Simple CRT, click on the Send menu, then on File. Select the text file for your simulation program and click the Open button. The program has a run statement and it will start running after loading the file. Click on the Plot menu, then Continuous. The program runs in real time and continuously generates data. The continuous plot mode will update the plot as data comes in. Scale the data using the edit boxes for a range of 10 and offset of 0. Up to 5 variables are plotted. The program also sends the data to DAC 0. The DAC output voltage is scaled to plus and minus 10 volts on the optional circuit card. Captured on an oscilloscope, the simulation result is very close to our analog relay circuit. More projects can be found at the GitHub page. Adios and enjoy experimenting.